Also dealing with sort of fuzzy data. So one of my faculty colleagues, Chen Li, who's here in the back, Chen, if you want to raise your hand so that you can especially ask him hard questions about this area. He's like a world expert in fuzzy matching. So you can ask him any question, he'll give you a fuzzy answer. But he'll, the answer's in there. He'll actually give it to you in small pieces called grams, and then if you reassemble them, it's the answer to your question. And so we also, in this world, data is dirty, queries are dirty, you're sort of speaking into your cell phone or typing in your cell phone, working sort of quickly on the web. Things rarely match perfectly. And so we also wanted to have sort of special technology in our system for dealing with that, and we'll talk about that. Everything is happening with locations when people enable that in their cell phones, so spatial data, simple spatial is really important, and everything has got times and dates associated with it, that's important. And so we said, as we build this thing, it should be sort of friendly for fuzzy questions and also deal with spatial questions and temporal questions, and do all this in the context of one shared nothing scalable parallel system, and so that was our goal. And then we're also doing some sort of novel stuff about what people are sometimes calling fast data or high velocity data that I'll talk about. And then obviously our real goal is, we're a university and our product is, they come labeled with BS, MS, or PhD. And so our product is graduates who want to train people sort of in big data technologies and in how to build systems of this scale. And so that's another of our main objectives. So you can see that we have sort of t-shirts that are sort of big data graduating training for most of the people wearing those. Okay, so I'm going to tell you about AsterixTV. Right before I do that, here's some of the things that we're trying to not lose as lessons from the world of Hadoop as we create something different. So one is, people like the price point. Open source is a great thing. The price is right, and so AsterixDB is being offered out with open source, no license restrictions, Apache-style license, because that's what the community seems to want. Non-monolithic layers, talked about that, so you can use the piece that you want rather than using the entire system if you don't need the entire system. We'll talk more about that. Equal opportunity access to data that has been stored in our system and data that's stored in someplace else, like HDFS, is important. And I'll tell you about how we address that. And then kind of on our roadmap, we've got low-level sort of technology in our underlying platform, sort of not yet rolled out to the higher levels of AsterixDB. Obviously, sort of the roll-forward recovery for long-running things in Hadoop is very important. It gets the job done eventually. In databases, we're more traditionally saying, kind of doesn't matter what happens, either as long as nothing happens or it all happens. I'll come to you and I'll say, life is good, I didn't hurt your data, I had to roll back your job or I rolled your job forward. Roll forward recovery is very important for large jobs when things fail during job execution and you need to get it done. So we're going to be learning from that and again have infrastructure kind of for that. And then it's also sort of one of the nice features of HDFS is you put data in and it finds a place to live. And those kinds of features need to exist also in more database-y kinds of storage. And so we're sort of have a roadmap kind of on that that's part of our current research agenda. So those are sort of the things that we took as sort of really good things that are in the Hadoop world that we need to not lose if we believe we're going to create something different. So this is a one-slide summary of AsterixDB, and then I'll tell you what it looks like for a user. This is kind of our architecture slide. So it's a shared nothing system. Each one of those boxes is a separate computer with some disks and some memory and some cores attached to it. It runs basically sort of an Asterix system instance. Those things are coupled together, and you can execute parallel queries much as a parallel database does. So at the bottom of this, there's a storage layer. The bottom two boxes are essentially Asterix storage, and I'll talk more about what they look like from a user perspective in just a minute. But essentially, we have technology based on what are called LSM trees, log-structured merge trees. Think sort of what's inside HBase for storing data in a B-tree kind of way and in other kinds of ways that I'll talk about. So there's like a storage layer that stores components of your data, and then those things are integrated into a logical concept that I'll talk about called a data set or a data feed data set. So at sort of the bottom two layers are data storage. Just like in the other pictures, there's a layer in the middle that does query execution. We have an execution engine called Hyrax that I'll talk a little bit about. And then on top of that, we take in queries in a language and compile them into Hyrax jobs. And we consult a metadata manager to understand things about our data, and I'll give you a clear picture, hopefully, of that stuff too. And so to a first approximation, that looks like a traditional kind of database architecture, but it's got a very different kind of data model, query language, and openness to it as compared to, for example, the relational system. And it also is a parallel sort of shared nothing open source thing, which is also something that you don't get in the world of databases today. You can get open source databases, but they're not sort of large scale parallel. And again, we'll have more, we can sort of answer questions more about that at the end. The basis for this are a data model called the AsterixDB data model, and I'll explain more about that, and a query language which is fully NoSQL compliant, right? So NoSQL is all the rage, but we have NoSQL here. We have a language. It's a query language. It's called AQL. It's not SQL, so we can check the marketing box saying we're a NoSQL system because we have NoSQL. We have data coming in through loading the data or feeding the data from external sources or from inserts or deletes happening through the AQL query interface. You can ask questions through the AQL interface. They can be little questions looking up sort of points of data, medium-sized questions looking up ranges of data, or large questions doing large correlations across multiple data sets. All those things are within kind of our target for the system. And then we kind of have the dotted box in the future. We would also like to support like continuous queries and data publishing from the system. That's another research agenda that we have. And I'll talk a little bit about that at the end. Okay, so user experience time. So what if you were to, as all of you are surely to do, download the system sometime tonight, because you can't wait till tomorrow, because you might get one of these, right? So you'd get the AsterixDB data model as the way of thinking about your data if you get our system. And so what is the AsterixDB data model? It's basically kind of the world of data as you see it when it's in our world. In the world of databases, you create a database. This is, sort of 2013. Databases have been around since the 70s, and so no more databases for us. You have a dataverse, your data universe. And so you create a dataverse. It's a place to put all the data that's sort of related to something you're trying to do. And so we have a demo that ships with the system. This is sort of descended from that. So you might create a dataverse called Little Twitter Demo, easily written and said. And you would create that dataverse. It's now a place where you can create a whole bunch of things that you want to store that might be about this demo that you're trying to create. You can create data types. And so if you know some things about the data that you're going to be dealing with, you can tell the system about them by creating data types. And then you can create data sets to store that kind of data. And so this is a fairly complicated looking example, and I'll simplify it in a minute. That is what you might store if you're sort of camping on one of the Twitter APIs and getting the stuff that's being fed to you in JSON form. It feeds you things that look like this. So a tweet message, what this says, it's kind of like a Java class or pick your favorite language, a little bit like a database schema, but it's a richer kind of language. You would create a type called tweet message type for this data as open. I'll talk about that in a second. With a tweet ID, which might be the unique identifier of the tweet, which tweets have. Might have embedded in it a little nested record that has information about the user. So in this case, their screen name and the language that they're tweeting in and how many friends they have and so on. That snapshot of that information gets sent with the tweet. And then you might have some other information about the tweet, like where did it happen, the sender location. That's marked as a point, so that's sort of a two-dimensional piece of spatial data. It's marked as question mark because it's optional. That's our way of saying nullable. So a tweet might or might not have that. Not all tweets. In fact, the majority of tweets aren't yet location sort of tied, but more and more hopefully they will be, so the businesses can sort of do what they want with that information, and so can healthcare organizations and so on. Tweets are tweeted at a particular time, so that information is there. A tweet might be about a set of topics, and so might have a hashtag like AsterixDB, hint, hint. And so that tweet, one of the referred topics might be AsterixDB. And so that you might have that set of topics, a bag of strings essentially, attached to this piece of information that you're going to store. And then probably you should keep the whole thing, because if you didn't extract what you want, you can go back and look at it tomorrow. And so the whole message, the whole tweet message might be stored as well. So for whatever application you're building around tweets, this might be what you've decided you'd like to do. And now you need to create a place for them to live. So that just says what they look like. Then you have to create a place for them to live. And so you'll create a data set. That's sort of the table-like concept that we have. You have data sets that are typed. And so the type is tweet message type, and the data set is called tweet messages. And all we require you to say, kind of in addition, is you need to tell us, like, what's the unique thing about a tweet that I can use to find that tweet if you ask me. So to sort of think key value store in a way, you have to identify, like, the main key, the primary key for the tweet. And we use that under the covers to partition tweets across a large cluster. So we do some hash partitioning today on tweet ID. And so this would create that type, and that would create the set of messages. So a little bit more about this. So first of all, our model, so where it came from is looking at JSON, which is very popular these days, and saying, what if we made JSON a data model? Thinking as database people, what's it missing? Well, it needs to have a richer set of types. We need spatial and temporal and so on, in addition to the basics that it has, because now it's a data model. It's not just a transition format from one machine to another. We also would like to be able to have sort of rich constructors to build up interesting types. And so, this example has a nested record and a bag of strings. So we have records, lists, and bags, and you can compose them arbitrarily to create interesting objects. We have an important idea, we think it's sort of an important idea, of having open types. And that's the default if you don't say. If I just say create type tweet messages, it would be open. I can say as open or as closed. If I say as open, what I'm saying is that's what all tweets will have. They'll have a tweet ID and that user info. It might have a location. If they do, it'll be a point. So I'm telling you what a tweet will have. It could have a lot of other stuff too. So it can have additional attributes. That's okay if it's an open type. And so the type spec is kind of like, it'll have at least this stuff, but it could have more. If you would like to have something more like a relational model where your data is what you say it is and nothing more, then you could say as closed, and then we wouldn't allow additional attributes to be on your data. But if you say as open, everything that's a tweet message will have that stuff, but it could have anything else too. And then finally, we have a notion called external data sets, where instead of actually saying what you say here, in which case we will create storage and manage storage for your data, you could actually make what's called an external data set specification, and you can see examples on our website that I'll point you at later. And you can point at data that's in HDFS, already being sort of accessed by Hive, and we can access it too. Or point at data that's stored on your local file system that maybe is in a delimited file, and we can access that as well. So you can create a data set that accesses external data, not just stored data. And then we have a notion called data feeds that I won't elaborate on right now because I'll get to it in a couple slides. So that's our data model. So we've invented sort of this basically, so we think it's a common sense sort of extension of JSON to be what it would be if you wanted a data model for that kind of data. So semi-structured because if you wanted to, you could just say this. You could say, I want to create a type called tweet messages with a tweet ID, and there's going to be other stuff, but I'm not going to tell you ahead of time. That would be fine too. You can just say that much and start your project and build your app, and your app would run just the same as if you'd done the other thing. The thing is, when you went back to think about what was in your data set, you wouldn't really know because it could be anything. But you can choose. So if you like a world where you don't want to prescribe ahead of time what's going to be in your data sets, we support that world. But if you know what you want, you can also tell us upfront, I should say, that you're going to do that. And if you do tell us this information, we'll exploit that. We'll separate out the schema information from the data, store it somewhere else, and not every piece of data will carry all that information. But if you tell us instead this, you can still store the same data, but each piece of data will have to know what's in it. The data items will be bigger because they'll be carrying your schemas as well as their data. Your choice. We'll support both. And so that's kind of the openness that we think is important. Again, the idea is the semantics of your app and all your queries and everything else will be the same regardless of whether you say the first thing or the second thing. If not, you can file an issue on our website, which we'll point you at later, because that's how it's supposed to work. Okay, so this is just an example of some tweets. We won't go into the details there. We have a query language, AQL, the Asterix query language, and this is like a first example of a query. So suppose you wanted to know, like from that data set that we created a slide or two ago, what is the user information and what did they say for all the tweets that are related to, actually this slide is slightly out of sync, that are from the user whose screen name is dflynn. Okay? And so what you do is you declare a variable called tweet. You say for tweets that are in the data set of tweet messages. So that specifies that you want tweets from that data set. It binds that variable, think about it sort of one at a time to those tweets, checks to see if the tweet's user record's screen name is dflynn24. And if so, it'll create a new instance of our data model, which has two attributes. The first one is called tweeter, and that'll be that user's record. And the second one is called tweet, and that'll be the message text. And so you've got a bunch of sort of stored data. You want to create some summary or some other kind of data from it. You can express that in our query language. And so it has a whole bunch of features, and you can learn about that by sort of looking at our beta. It has a special support for similarity matching. I'll talk about that in a second. It supports spatial predicates, so we could have said something about the location of the tweets if you wanted. You can do aggregation. I'll show you that on the next slide. And there's more sort of in the works in terms of features we expect to have. But it's a pretty rich query language. It was inspired by sort of looking at what's in the language X query, which deals with the semi-structured data of XML, and throwing away a whole bunch of stuff that's XML specific or kind of crufty, keeping the core ideas from that language and then sort of making that a new language for querying this sort of JSON extension kind of data that we have. So that's sort of a quick introduction to AQL. If you wanted to do something more complicated and say, okay, so people are tweeting about stuff, tweeting about AsterixDB today. They're tweeting about Verizon because of the news, and so sort of if I wanted to go through and find what are things people are tweeting about in those Verizon-related tweets, what are the other topics, and I want to know like how many things are about that topic are being tweeted, you can express that as well. I won't take you through the details, but it requires a variable that looks at the tweets, a variable that looks at the topics inside the tweets, kind of flips them inside out and says, okay, group by the topic, and then tell me like what's the topic and what's the count. Detail is sort of unimportant for getting you the idea of the kinds of things you can do, but then you would get back, okay, for the Verizon topic, there's 3 tweets. For topic commercials, there's 1 tweet, and this is sort of how many from the slide 2 slides ago would have satisfied that. So that gives you a rough idea of the kinds of things you can do. So you can sort of slice and dice your data and aggregate and so on, restructure, and get something new of a different shape with different information out of that across multiple data sets potentially. Okay, special support for the case where things don't quite line up. And so if you wanted to look at tweet messages and sort of ensure that the tweets are not the same tweet, so there are 2 messages in the tweet data set, same data set with different IDs, but the text is kind of the same. And so the red operator is our kind of equals operator. That sort of says, I want sort of rough equality rather than actual equality. I want a fuzzy match between those 2 messages. There's a way of sort of controlling what that fuzzy match means, but for string data, it means edit distance with some default parameters that you can also control in the context of this query. What this will do is find pairs of tweets that are similar, message text-wise, similar in terms of their content, and show you that pair, so you could look for things that are similar. You probably want to restrict this a little bit, because you can get a lot of data back, potentially, if there's messages that meet that similarity criteria. Okay, and then finally, sort of future work that we have, there's a secret feature inside our system, which we haven't documented yet, called data feeds, but it's running in the lab, where if you would like to have data continuously coming into your system, you can create, instead of a normal data set, you can create a feed data set. It's just like a normal data set in most ways, except that it's sort of attached through an adapter to some outside source of data. And so the first example there is creating a data set that is sort of attached to the Twitter stream using a Twitter adapter with a sampling interval of 10 seconds. There's, for feed data sets, the opportunity to specify a function that gets handed the tweet on its way in, that can process the tweet and add information to it before it's being stored. And so you might have a function that's adding hashtags to tweets, looking for those hashtags and putting them into that sort of referred topics attribute. And then the rest of the properties are the same. So you say what's the key, and it'll be partitioned by that. Likewise, you could build something for other kinds of sources, for example, CNN newsfeed. You can also, just like regular data sets, you can index these data sets, and so you could create a location index on sender location of tweets. We support B trees, R trees, which are a spatial index. We also support sort of inverted text indexes. And so you can sort of use a rich set of different kinds of indexes to index your data so that queries can be then efficiently processed if they have location predicate or a text predicate involved in them. And then once you've created these 2 feed data sets, you start the feed and data flows in. So this is different than data streams because data is not like flowing in and you have to catch it while it's there. This is a keep everything kind of feature. So this is basically kind of attaching a hose to a data set, and the data set's getting fuller and fuller while the hose is attached to it. And so it's a keep everything thing. It's about data ingestion, so you don't have to write a program that's kind of orchestrating the Twitter stream and doing inserts. You just hook a data set into AsterixDB, plug it in, data will come in. And all the queries that you would have done over that data set of tweet messages from before, you could still do over this data set because it's just the data set. Okay, so that's kind of the end of our user model. I just want to spend kind of the last few minutes of the talk giving you a quick overview of what's under the hood and why it's more like the Hadoop world and less like the database world, but also how it's different than Hadoop. And so again, we have sort of multiple layers, multiple components, and an openness that you don't find in the parallel database world. And so at the bottom, we have a data parallel platform called Hyrax that I'll tell you a little bit more about. That's our parallel runtime. That's our alternative to Hadoop. So we're not actually based on the Hadoop stack. We are sort of a peer, if you will, of Hadoop. And sort of the interoperation thoughts in terms of working with Yarn and so on. But it's a different execution platform, and I'll say a little bit more about that. At the next layer up, there's sort of a middle tier where there's a layer called AsterixTV, which is about sort of doing algebraic operations over big sets of big data. I'll say more about that as well. We also have a MapReduce compatibility layer that we've got running in the lab that we will open source down the road, hopefully fairly soon, where you can run your Hadoop jobs kind of out of the box on our system. and it's sort of emulating Hadoop, but sort of more quickly than Hadoop in this world. And then we have some other byproducts that we've done that we can tell you about kind of after the talk if you're interested. A lot of people these days are interested in dealing with big social graphs and doing big graph analytics. And so Google published a paper called Pregel, and being open source people, we said, okay, that looks like a software specification to us. And so one of our students who's here tonight, who can talk to you afterwards, basically built a clone of Pregel using our Hyrax technology, and it has very good performance and scalability. So if you're doing big graph processing, ask us about Pregel. It's part of the AsterixDB family of software, I guess. And then if you're doing big machine learning, we're doing some joint work with UC Santa Cruz around big data support for machine learning. There's a thing called iterative map reduce update that we're doing with them that also runs on the Hyrax platform. So there's a bunch of work sort of using that same platform that we've developed. That's the oldest part of our system. Work on that started in early 2009. So that piece is relatively mature compared to pieces that came in later, which have been under development for fewer years. And then at the top, again, we have multiple components. The green thing is AsterixDB, our system. It's what we're giving you sort of tonight, sort of making open is the AsterixDB system, which has the Asterix query language at the top. And so if you talk to us through the green thing, that's kind of your database stack. But you can use other components. And people have built other things. And so the same student who was working on sort of graph analytics also, we did sort of a demo for Facebook where we took the Facebook Hive system and sort of pulled the bottom out from it and plugged our system underneath that. We can tell you more about that, creating the thing we call AsterixTV, which is essentially Hive running on Hyrax. We've done that sort of using this algebraic layer. And then people have sort of talked about how you would build other high-level language compilers. There's an Apache project doing something called bxquery, which is the big parallel xquery implementation, also using the red layer AsterixTV and the blue layer Hyrax. And so I'll sort of tell you a little bit more about each of those pieces before we wrap up. So let's sort of go top down. So the green thing I told you about, that's AsterixDB, and we'll tell you how to find out more about that. The next layer down is for those of you in the audience, and there might or might not be any of you, who are thinking, I've got a great idea for the next big data language, and it's not this nonsense I'm listening to right now. It's also not SQL, it's something else, and it's going to be great for processing this other kind of data. If you're trying to build a big data language, there's a bunch of stuff you have to do that we've had to do several times, and that others are having to do. Everybody who builds a big data language has to do a lot of stuff in common. So they have to have some sort of a data model. They have to have physical operations to process data. They have to have an optimization framework if it's a high-level language. And so what we've done kind of with the red layer called AlgeBricks is to factor that out into a reusable component where a bunch of that stuff comes with AlgeBricks. And then you can add things that are specific to your language. And so instead of writing, sort of 50,000 lines of code and making up a number, you can borrow 40,000 and write the other 10, essentially. So you can write sort of, a piece of something that you would have had to write all of. And so that's been the goal of AlgeBricks. And we drove that out of sort of creating this HiveSterix thing from AsterixTV, factoring out the sort of data model independent stuff. And so this is just a piece of technology I'll tell you about. It's under the hood, but if this sort of resonates with something you're trying to do, we can talk to you more about that. Ultimately, AlgeBricks stuff turns into things that are executed on the Hyrax platform. Hyrax itself, it's actually, so the upper right corner, those are Hyraxes. It's actually, so there's a website that we have for Hyrax. There's a video link there, you can go learn about them. They are the closest living relative to the elephant, so chosen for obvious reasons. Except they cluster well, right? And they're really cute, so how can you not want that, right? You can't leave today without having one of those things, right? They make a great pet. An elephant, have to clean the backyard would not be so great, but those things, they're smaller, right? So, fewer droppings and things. And so that's a Hyrax, and so actually that's what our Hyraxes look like. That's part of our logo. It's a partitioned parallel platform for data-intensive computing. So what does that mean? Basically, we're using the same kinds of ideas that are inside parallel databases and also inside Hadoop to deal with large amounts of data. A Hyrax job is a DAG. It's not just map reduce, job over. It is a whole sequence of operators. And it's not just a string of linear operators, map or reduce. It's actually can be sort of a filter operation followed by, with another filter operation in parallel, feeding a join operation, feeding an aggregate, things like that. More complicated things that look like sort of the query plans that parallel databases use to do things more efficiently. So operators, the boxes, they consume and produce partitions of data. And then connectors, the lines, route data, repartition data, based on things like hashing, or just hand it to the next guy, or range partition, or other kinds of repartitioning, or replicate this information. There are various kinds of connectors that can be used to connect the operators. And so a Hyrax job is sort of a rich sort of data flow program, essentially, that is then executed in parallel on your cluster. How does Hyrax compare to things you might have heard of? So sort of it's based on using parallel database ideas and applying them to sort of the big data world. And so it's using well-known ideas, but packaging them in a way that's sort of very componentized and reusable, as opposed to being just inside some system in a layer that you're not allowed to touch. Versus Hadoop, it's a more flexible model. It's a DAG model with rich operations that have multiple inputs, as opposed to just map and reduce. And it's also a much less pessimistic, I think you could say, implementation. What Hadoop does is, in order to run very large jobs for very long periods of time, under sort of conditions where disks might fail because your job is taking 8 hours and 6 hours in something goes away, it sort of tries to persist everything. Every time you do a map reduce job, writes the result to HDFS. Sort of in between map and reduce, it always sort of has files going on. So rather than sort of pipelining things, always sorts the data. So it's a rigid model that works really well, but it's a rigid model and not necessarily the most performant way to run a query. And so our system supports a model like that, but also supports much more sort of rapid pipeline models as well that can be used to get much better performance on queries. So it's not difficult to sort of run much faster than Hadoop if you don't use sort of the same pessimistic implementation. MapR guys will tell you the same thing. And then what about Dryad, which is from Microsoft, which was for a while a contender. Microsoft is actually now doing Hadoop as well. But basically Dryad, sort of a circles and arrows model, but they didn't have a notion of data and data flows and sort of out-of-the-box operators. So this is sort of like a level above Dryad. So this is where sort of Hyrax sits in the ecosystem of big data runtimes. Okay, so wrap up. So why would you maybe want AsterixDB? Well, because we think we're like a one-size-fits-a-bunch solution. So we think we can give you better functionality and manageability and performance by giving you one system that you can use to solve a bunch of problems that you would have had to get maybe Hadoop and Hive and MongoDB, as in the UC Irvine med school example, to solve in the past. And so what do we have inside that maybe would give you hope that we could do that quickly and effectively? We have sort of indexing technology and storage technology based on log structuring techniques that can ingest data quickly and then can still sort of run queries over that data. We have support for spatial data, including R-tree spatial indexes, support for fuzzy data and indexing fuzzy data to do sort of quick lookups, support for external data sets and also data feeds coming sort of in a future release. And again, we're sort of working on that quite actively right now for getting external data. And then there's also this sort of graph processing thing that we can tell you about offline if you want, called Pregolates. And then underneath that, we have this Hyrax engine, which has been sort of scale tested out to a large number of cluster nodes, at least from our perspective. I'll tell you more about that in a second, at Yahoo. And it's a very powerful, very flexible system. And again, we'd be happy to tell you more about that and sort of point you at papers and show you how to get the system. It has construction inside based on sort of best-of-breed parallel database ideas. It's not just sort of a simpler engine. And in some of our tests for disk-resident data, running on data that places systems like Hive have stored, if we can run our queries on the same data, we get large performance gains. Sort of a modest sort of middle gain might be 10x. So if you're doing certain queries where we can use indexes and they don't have them, we could sort of beat them arbitrarily. But on things that they're good at, we can sort of do 4 to 10x their performance. So we can again tell you sort of more about those results if you're interested. So that's our motto. So more engine, less trunk. Also sort of chosen for reasons that, if you don't get it, that's fine. But think about it. And so AsterixDB is sort of coming out. Where can you learn more? We're like the new kid on the block. And so let's actually, click on the link. You can go here. And this is our website. So if you come here, you can get an overview. We have all of our sort of documentation online. Tells you kind of what our system is and more about it. And so there's information about how to get it and install it. There's a sort of a 101 that will take you through a whole bunch of the features. There's a reference guide to the data model, to the query language, to the functions, and so on, that the tired-looking team in the shirts have been working on. And so, we invite you to come to this site and sort of check it out, download it, play with it. It's intended to run on clusters, but it will run on your laptop as well. And so get it and try to run it on your laptop. And remember, sort of actually getting into the user group and getting the system. And it's a way to get like one of these, right? You want one of these. And so anyway, we'll come back to that. So that's the website. So you're welcome to go there. So where are we? So basically, we started the project in early 2009. We had a little bit of seed money from eBay, and we had money from the state of California. We got a big NSF project that we did jointly with UC San Diego and UC Riverside and UC Irvine that has been running with UC San Diego, doing research on sort of text kinds of things, UC Irvine focusing on the core system, UC Riverside focusing on aggregation, and also some interesting semi-structured kinds of things. All this stuff has come together into a sort of large, and what we believe is sort of an industrial quality code base as a result of the project. So it's actually, at this point, sort of a fairly large, significant piece of code. It's been tested. It's what we would consider to be scale. What Yahoo would say that's, that's a spare cluster in Yahoo Labs, but the cluster has 1,400 cores and 700 disks, and we run queries at that scale. We actually did a rewrite of parts of our Hyrax system to run successfully at that scale, and so it's sort of ready to go up to that point. We haven't gone beyond that point as of yet, but we believe we have something that scales. Hyrax and Pregolix have been around for a while. Hyrax is something that sort of a few experts elsewhere have been playing with. Pregolix is the graph thing that we'll tell you more about offline if you want to know about it, which is available and sort of intended for end users who have graph problems to download. And AsterixTV is here. So it has a NoSQL style data model with a not SQL query language. It supports declarative queries, runs them in parallel. You can insert data and delete data, and all that stuff is affecting stored data in the LSM world, or also you can deal with your external data through our external notion of data sets. Has some cool features for fuzzy, spatial, and temporal query processing. And we also have I guess we'd say, key value style transaction support, sort of NoSQL-like support for doing inserts and deletes and knowing that your data has gotten there or not. We can tell you more about that as well if you want. So this has been a huge effort of a lot of people, only some of whom are here, but all of whom deserve credit. And so faculty here, myself and Chen Li, and research scientists here, Vinayak Borkar, who's in the room, who's sort of the Hyrax guy, and Nick Knows, who was here for 2 years from UC San Diego and has now gone off to Google. UC Riverside, we have a collaborator who can't be here tonight because he's giving his last lecture. This is the end of the quarter in the UC system, Vasilis Tsotras. And from Oracle Labs, who's also here, recently joined the project, Till Westman. So Oracle is collaborating with us around this by letting Till work with us and work on this. A whole bunch of PhD students listed here. I won't sort of read all of their names, but a couple of alums have gone on to HP Labs and to Cloudera. What the Cloudera alum was part of creating a thing called Impala, which until today was interesting, right? But now we have AsterixDB. So sorry, Alex, if you're watching this later. And then we have a bunch of students who are here who we can introduce you to if you want, both from here and from UC Riverside. There's also an alum who did some work related to the project, who's at Google, who did some basically interesting text query kinds of things, Nathan Bales. Then master students, we've got a bunch of master students who've gone through and done projects. Actually, we have 3 things coming out today. One of them is a software, and 2 of them are our master students who just filed their theses successfully today based on work that they're doing in this project. We also have a couple of bachelor's alums. And then we have some work with sort of foreign affiliates, mostly in Germany at the moment, but also a bit in India, students elsewhere who are working on projects related to this. We've been collaborating a bunch with industry, trying to make sure that what we're doing is sort of not crazy academic stuff, but crazy industrial stuff. And so we've sort of worked with Facebook, talking to them about what are their problems, what's their architecture, what do they care about, what do they think about what we're doing, and so on. One of our staff, faculty-ish, graduate student-ish people, Vinayak, who's our chief scientist, basically got one of the early Facebook fellowships. They also told us a lot, gave him access to a lot of information about what the workloads look like on their clusters that have helped to inform us in terms of what we think about. Yahoo, we've collaborated with and gotten access to that cluster. They've also given money to some of our graduate students. We've done collaborations with a couple of other universities. And then also there's an Apache project building parallel X-query on our system. So we've sort of been talking a lot sort of with people outside. It's intended to be open source. For more information, if you want to know more, again, so you can go to our project page, which is up as of right before this. You can look at our code base at Google Code, either for AsterixTV or for Hyrax, or for Pregolix. You can go to that page and it will sort of take you into the world of Hyrax and its sort of other ecosystem. So that information is there. We'd encourage you to take a look at that. We've gotten funding from a bunch of places, and so National Science Foundation has been kind of our biggest funder. eBay got us started. Facebook has helped. Yahoo has helped with machine access and grants to students. We have industrial funding from Google, from HTC, from Microsoft, and a collaborator sort of donated by Oracle Labs. And so we've been working a lot with industry, and we appreciate the support we've gotten. And for those companies who are not on this list, don't you wish you were, right? Because you could get one of these shirts, right? You know, so anyway, sort of thanks to all of those. Also, we have some early adopters, and so this is actually my granddaughter this morning wearing the AsterixDB shirt, which you can purchase if you want for your granddaughters, or maybe your daughters, or maybe later for the grad students who don't have daughters yet, at Zazzle.com, right? So that's an option. Right?
Great.
Notice that is fashion, right? That's,
yeah.
If it's not, don't tell me because it's my granddaughter. I don't want to know. But anyway, so that's a current shot of our earliest adopter, like looking for a Hyrax, which is probably loose on the lawn. Okay, so that's it. That's our story. We've sort of taken enough of your time. We're sort of here. I guess we have the room until 8. We have a team so that no matter how many questions you have, we can parallelize and answer all of your questions. We can take them as a big math job, and then we can kind of reduce them and provide more information on our website if there are questions. And so at this point, I'll stop and take questions. Again, one last reminder. So one of the ways of getting a shirt is you can ask the best question that the people who have shirts already think was the best question. So questions about what we've done? Yeah. Go. Yeah, absolutely.
It's not a great question, but it's an important question to me. It's about streaming data analytics. Have you done any performance testing on your platform, and how does it stack up to the others?
Right, okay, so yeah, so the question is streaming data analytics, what do we do about streaming data, and what's our performance like? And so we're not trying to be like a real-time stock trading, streaming data analytics kinds of engine, but we're trying to deal with data streams and to do that performantly. And so for us, what that's about is our support for data feeds, which is you can sort of stream data into our system at high rates, sort of high defined by sort of data feed rates, not like microsecond, got to make this stock trade kinds of ways. We can deal with data streams, and we can run small queries over that data, or run larger queries over that data. That data is going into the system right now, and that data is available right now. And so we're much more kind of in the zone of regular databases than we are like the Hadoop zone, where the issue is, it takes a long time to initiate a job, and it's really designed only for batch computation. So our system is really aimed more at a range of use cases where that kind of batch computation, those large computations, we can do those, but we also have indexes. And that data that's sort of coming in those streams is being indexed as it's arriving. And now if you have a quick question, you're looking for the tweets in the last 2 minutes that have been about this topic, you can ask that question. We can exploit indexes to answer that. And so we're sort of closer to doing real-time-ish things, but we're not a real-time streaming engine. We're different.
So how does it stack in terms of performance to your...
So we haven't done any performance comparisons, and so I'm not sure how to give you sort of a meaningful answer, except to say that we're sort of in the milliseconds range when we're processing queries, or the hundreds of milliseconds range, as opposed to the seconds or hours range, which are more the size queries that you would target with something like a Hive or an engine like that. So if you're dealing with Hive, you're probably wanting to run queries that take at least minutes, if not hours, essentially. That's more the use case for those things. And we're designed for small queries as well as large. And so how we do that is because we index data, and we can answer small questions by looking at small amounts of your data. Whereas if you're dealing with sort of this straight Hadoop stack, everything you ask turns into essentially a scan of all of your data. And I think MapR probably has some interesting technologies that they're building as well that we'll talk to them about. But that's kind of what we're doing technically about that. Other questions? Yes?
So if you have a customer that already has a lot of legacy data, some SQL, some raw data, so what would you recommend? How would you interoperate with the existing SQL?
Good question. Yeah. So
would you migrate some of the other stuff to yours, or
right. So yeah, good question. So the real question here is like, what do you do about legacy data? And there's sort of two kinds of legacy data. There's like old legacy, which is sitting in relational databases. There's new legacy that is sort of sitting in files and sitting in Hive, essentially in HDFS. And so we're sort of working on that. So what we're doing right now is we have this external data set notion that I mentioned, where if you have file data or HDFS kinds of data, you can point us at that, and we will look at that as being an external data set. And you can run the same kinds of queries you could run over data that you put in our system over the data that's sitting in those files. So that's the good news. We can actually access your external data. Sort of the other good news is that if you wish your data were in our system because you want it to be indexed and you want to do a quick query, we can solve that problem as well. You can basically write a query that does a for over your existing data and selects the part of it that you care about and inserts that into one of our data sets, and then it will be parallelized and you can run queries. So you can sort of migrate data into our system from sort of new legacy data out of HDFS or files in that way. And we can run queries just over it where it is. The problem is that if it's in HDFS, we're kind of limited to the same thing that Hadoop is limited to today, which is that you have to sort of crawl over all the data to answer the question. And so we're also sort of working on, starting this summer, kind of another answer to the new legacy data problem, which is to make it possible to build indexes over data that we don't own. So today, all of our indexing technology, our secondary indexes, our B trees, our R trees, our text indexes, you can index our data, but you can't index if it's in an external data set. We will fix that. And so then we'll have even a stronger story for new legacy data. For old legacy data relational, we're actually not working on that yet. We know that there's interesting stuff that we could look at to do there. We actually, the last of these OC hugs, sort of talked about how Microsoft was thinking about dealing with mixing new legacy and old legacy together. We're not doing that at this point in time. But we could look at doing that as well potentially. But we're really right now sort of more after the semi-structured data world, and so our first kind of legacy data that we're trying to go after is the data that is in the new legacy like Hive or P kind of storage. Other questions? All right, so the team is here. Those of you wearing shirts, oh, sorry, was there a question? You pointing at someone who had a question? I saw an indirect reference to a question. Nope, okay. So the team is here. We'd be happy to sort of tell you more about the system, answer questions. We could even, I think there's one team member who's ready to maybe give a demo, we'll see. And so, if you'd like to see the system, sort of an application running, we can show you that as well. But we would encourage you strongly to go and download the system, give it a try, and if you're interested, talk to us more. We'd love to work with local companies. So, thanks.
Free shirts for both.
And, oh, yes, right, okay, so our shirt criteria. What we'll do actually, so Zach, who spoke up, will be the getter of shirts.